I'm very pleased to welcome Alexandre Bône. Oh, I don't know whether. So, I'm going to talk about learning distributions of shape trajectories from longitudinal data sets. Thanks.
Thank you very much for the introduction, and I would like to thank also warmly the Isaac Newton Institute for having me here. I'm delighted and really enjoying a lot this week.
Could you speak up a little bit, please?
I'm delighted to be here, and I'll try to speak up. So yeah, I'm Alex. I'm working with Stanley Durrleman and Olivier Colliot in Paris within the Aramis lab, which is an INRIA team. And I would like to talk to you today about longitudinal data sets. So I will straight ahead place myself within the deformation-based statistical shape analysis. So this field has addressed two questions. First, if you have a cross-sectional dataset of shapes, so here you have 4 individuals, the usual procedure, which is the one presented by Nina just before, is to estimate a mean and a variance structure of these datasets. So the template shape estimation, that is what called just before, can also be called an atlas. This is a very standard procedure that is used in statistical shape analysis. If you have a time series dataset of shapes, there is also a very standard analysis, which is to perform a shape regression. So you obtain a smooth deformation of a template shape with time. The next question for this field is how to deal with longitudinal datasets. So a longitudinal dataset is the repeated observation of several individuals over time. So here is an illustration, and you can see first that there is a variability in the geometry of the individual. So each individual has some particular features which can be seen here on the legs, for example. Some are tilted to the right and some are tilted to the left. A second variability is in the dynamics of the time evolution of those individuals. You can see, for example, the third individual starts to raise his arm later than the other ones. What we propose to do is to try to estimate the distribution of trajectories. So a first step, abstract step that we would like to take is to be able to reorganize those individuals according to a common time. So without introducing further mathematics, it looks like that. We would like to be able to sort individuals according to a time. Once we have aligned those individuals according to time, we can bring them all together. And the next step we would like to take is to average the geometries of the individual, and in this way be able to reconstruct a mean trajectory of this dataset. So this would look like that. And finally, another objective of the method we are presenting today is to be able to reconstruct the individual trajectories of the individuals. So here in red are plotted the initial observation, which were used to estimate our model. So summarizing up the objectives, we would like to perform a spatiotemporal analysis of trajectories, which can be seen as a mean variance analysis of trajectories. So first we would like to estimate a mean, and this will be encoded through a geodesic flow of shapes. We would like to assess the variability in the dynamics of our individuals. So we will use some reparametrization of time. And we would like finally to estimate the variability in the geometry of the individuals. And for this we will introduce a later concept of parallel curves on a manifold. And yeah, I would like to point out as well that we want to estimate all of that simultaneously. So this is the outline of the rest of my talk. I will first present the deformation model that I'm using, so which is a particular case of LDDMM, and then the statistical model, and finally some results. Starting with the deformation model, we are using a control point formulation of LDDMM. So taking a very simple approach, We choose control points of the ambient space, so either R2 or R3. We take some momentas, which are vector, on those control points. We prescribe the Hamiltonian equations, which are written here. And then we can integrate this system of equation to obtain, well, a trajectory of those control points and momenta with time. Taking the convolution by a Gaussian kernel, or whatever kernel you like, of those trajectories of control points and momenta, you obtain a trajectory of vector fields. And finally, we can integrate those vector fields in order to obtain flows of diffeomorphisms, as it is classical in LDDMM. Here we use a finite number of control points. This choice allows us to obtain a finite-dimensional Riemannian manifold of diffeomorphisms. And the flow obtained by this procedure is a geodesic of this manifold. Some example. So I talked earlier about geodesic regression. So we can use this framework, this control point formulation of LDMM to perform a geodesic regression. Here I have written the cost function that we are minimizing when we estimate the geodesic regression. So you can see here, noted C0, the initial control point that we will estimate, the initial momenta M0, the initial shape, template shape. I note the geodesics as exponential, so this is the Riemannian exponential of on our manifold, and it is integrated since from the time t0 the control points C0 and the momenta M0, and we integrate this geodesic until time tj here. The observation and noted y, and finally there is a regularization cost in order to obtain natural deformation when we estimate our geodesic regression. We can estimate this geodesic regression by gradient descent, and here is an example in 2D. So we have a time series of curl shapes, and we can estimate this regression that is plotted here. A second example here with brain structures. So those are meshes of hippocampi, putamen, and caudate brain structures, seen from both from a face view and a back view, and we can estimate a regression of the structures based on the observation of several MRIs of a patient. An example of atlas construction. So I will not. The notations are the same. The only thing I would like to point out is that now we don't have only one initial momenta, but one initial momenta for each subject. Minimizing this cost is equivalent to compute, or comes down to compute the Fréchet mean of our observation. And this can be done by gradient descent. And apparently it's biased if you do it this way. I would like to point out that it has been reformulated as a generative model, a hierarchical atlas model, which has been as well presented by Nina just before. So we can see this atlas model as first taking a template shape, which is a population variable, and then taking individual momenta, and finally obtain observation. We obtain here the formulation of what I will call the Bayesian atlas statistical model. We can, here are the parameters that are classically noted, the theta and the latent variable z. And if we want to perform a maximum likelihood estimation of our model, this means that we want to maximize this distribution of probability, which is a probability of observing our data set given some parameters. Two possible ways once we have formulated this hierarchical model. Either we approximate this integral as its mode, which is the max-max approximation usually done now in shape analysis. And we can note that taking the log of those probabilities, we obtain a very similar cost, or actually the same cost that I have introduced before. So approximating this maximum likelihood estimation comes down to what I've introduced just before. And so this is a Frechet mean that we can estimate by gradient descent. The other way to go is to perform an actual maximum likelihood estimation. And here we would like, the only solution is to use an EM-like algorithm. An example, we take the 5 previously introduced scores, and this time we consider them as a cross-sectional dataset. And we can compute the mean here, bottom left, and parameters of variability, of geometrical variability, which are the momenta. Going back to my initial problem of modeling longitudinal data, what we truly want to do is actually combining the two previously introduced approach. We want to do, in a way, both an atlas and a regression. So, just for fun, this is what it would look like. To be able to do such an analysis, we will use what we call the X parallelism on a Riemannian manifold. So take a geodesic, let's call it gamma. It's parameterized by the initial momenta n0. Take now a second momenta at the control points C0, which I will call the space shift Wi. We can parallel transport this space shift along the geodesic using the parallel transport operator on a Riemannian manifold. And then we propose to take the exponential of this parallel transported vector to obtain finally a transported curve that I will note eta. This is the main tool that will allow us to personalize not only one observation but a full trajectory from one reference template to to the closest point to the observations. A slide to say that to compute the parallel transport on our manifold, we will use the Fanning scheme, which is based on Jacobi field identity, first plotted out by Laurent Younes in 2008. And the interesting thing about this scheme is that it only requires to compute geodesics, which is to compute Riemannian exponential on our manifold. Computing geodesics is quite easy. It's a forward scheme. What we don't want to do is to compute log on our manifold, which are very expensive, and we don't control the error on them. An intuition of what is X parallelism on our manifold of diffeomorphisms. X parallelization allows.
Can I just make one remark?
Yeah.
This Jacobi field thing, it's not me. It's just copied from the Arnold's book.
All right.
Last chapter. Very nice description of parallel transport.
Okay. So using this notion of parallel transport, which we are now able to compute on our manifold, we can compute X parallel curve on our manifold. This X parallelization procedure allows to transport a check trajectory from one geometry to another. So here are plotted two individuals. The top one will be transported to the bottom one. You can see that the geometry of the target subject is respected in the sense that the legs are tilted the same way along the trajectory, but the transport of the time evolution of the source subjects is translated in its geometry. The blue momenta are encoding the geodesic that we are transporting, and the red momenta are the space shift sending the top frames to the bottom frames. You can see that the red momenta are transported by the blue momenta, so as we would like, as expected. Now we have introduced all this deformation framework, we can construct our statistical model. So we propose to use a hierarchical statistical model. At the population level, we have a mean trajectory. This average shape progression gamma is encoded by control points, momenta, and a reference time. At the individual level, we take space shift parameters that encode for the variability in the geometry, and time reparametrizing functions that encode for the variability in the dynamics. And finally, from this hierarchical model, we are able to generate observation. Another way of presenting my model, at the beginning there are control points. Those control points gives us our manifold. I take also a reference time t0. I take an initial momenta m0. So all of those are population parameters. From those population parameters, I can construct a geodesic. This is the first building block. Now I can sample acceleration parameters and time shift parameters that encode for the variability in the time dynamics. And those parameters allow me to compute for each subject the function psi, which is an affine function with time. And I will use that to account for the variability in the dynamics. I will generate the space shift Wi by this procedure. I'm saying that my space shifts are obtained by the matrix multiplication of matrix A with some source low-dimensional parameters noted S. And a technical point is that I want each column of my matrix A to be orthogonal to my initial momenta M0, so that the geometrical variability of my individuals cannot be confounded with the time evolution of my population. And finally, from all of that, I'm able to construct individual parallel curves to the source geodesic here in blue, and to reconstruct the closest possible the observation. So the statistical model could be given this way. You are given my parameters theta that I will estimate, and the latent variable z, from which I will obtain distribution of probability. I propose to estimate this model with a stochastic approximation of the EM algorithm. So this is necessary because of complexity of the model. So I perform a maximum likelihood estimate with this algorithm. And I would like to point out now three tricks that allowed us to accelerate the convergence of this algorithm, which is quite slow if you don't do any of those tricks. So we use an adaptative sampler, which allows to automatically tune proposal variances. We use a specific sampler on shapes, and we use an idea of log likelihood tempering, which has been maybe not introduced, but which has been given by Marc Lavielle. The idea is to not optimize directly on the target distribution, but take a smooth version of this distribution in order to faster go to the largest potential of this landscape. That was super clear, but the idea is coming from the simulated annealing algorithm. The code is available on this website. It is C++. So now I can present some results. I will start with simulated data, and then I have some real data in the context of Alzheimer's disease. So simulated data, I do not wish to spend a lot of time. It's converging satisfyingly close to the truth, and the algorithm has a stable behavior. Here are plotted the evolution of the error on each parameter with the iteration. And the algorithm is run 10 times. Each color corresponds to one run. And you can see that the same behavior can be expected at every run. We do not converge exactly to the true parameter because we have a finite number of observations, and also we are in a Bayesian framework, so we are biased by our priors on those parameters. Though we converge satisfyingly close, and this figure was shown already, that demonstrates two things: the ability of constructing an average progression from a longitudinal dataset, and the ability to personalize this mean progression and reconstruct individual progression. So now I've applied this method to real data. The data I used is extracted from MRIs of patients that develop Alzheimer's disease. At first, they have some memory complaints. They are what we call them MCI subjects, which stands for mild cognitive impairment. And those subjects, I take 100 of them, develop the disease within our observation window. So I take 100 subjects, and longitudinally this corresponds to 760 MRIs, because I have an average 7-8 observations per subject. From those MRI, I extract a mesh, which is the mesh of the hippocampus subcortical structure, and it looks like that. This structure is interesting because during the course of Alzheimer's disease, it is atrophied, well, it is known that it is the first subcortical structure to be modified in shape with this disease. So here I plot some observation for random individuals. You can see that it is very noisy. And here is the estimated mean progression on this longitudinal dataset. I have plotted the color corresponds to the norm of the velocity field on those meshes. But what I truly estimate is only the shape of this hippocampi. You can see, I think the main thing to observe is that we retrieve this atrophy evolution with time. I'm not a medical expert, but this is expected when developing Alzheimer's disease. So I had chosen some sampling. I can go for an even finer sampling of this trajectory. And we have here a trajectory with time. What I can also look at after estimation of this model is the evolution in space. By that, I have plotted here one component of geometrical variability among individuals. You can notice that the shape at the intersection is a reference template. And with this figure, you can understand that we are estimating a time evolution as well as a geometrical variability in our population. So that was the estimated population parameters. I can also play a bit around with the estimated individual parameters. And for example, here are plotted the true age of diagnosis, so that has been given by a doctor, versus the estimated onset age, which is T0, the reference time I have estimated, plus the individual time shift to I. This onset age captures at which moment the individual will start to develop hippocampal atrophy. You can see that there is a good accordance of those two distributions. I think the R square is 0.74. And this means that there is a strong correlation between developing cognitive symptoms, having troubles of memory basically, and the structural loss of shape or atrophy, the structural atrophy of the hippocampus. Here, I look at the distribution of the acceleration factors, which I have estimated, and encode for the variability in the pace of progression, the pace of hippocampal atrophy, versus the gender. And I'm able, with this plot, to find the statistical difference between male and female. Here, this means that female develop a faster hippocampal atrophy when they develop Alzheimer's disease on my dataset. I continue to play around. Here, I look at the distribution of the onset age versus 3 categories which are based on genotype. You can either have non-APOE4 allele, 1 allele of APOE4, or 2. This gene is known for years now to have an influence on Alzheimer's disease. Basically, having this gene is not a good sign. And here, I can retrieve or demonstrate a statistical effect of this genotype on the onset age of hippocampal atrophy. So meaning that if you have 1 or 2 allele, there is more chance to develop an earlier hippocampal atrophy. Finally, a bit more subtle analysis. Now I look at the source parameter that corresponds to this mode of variability among an individual. I'm trying to link the geometry of the hippocampus shape with the onset age of the atrophy. So from my onset age distribution, I make 3 categories. Either you are an early onset, so which is the 3rd percentile, 30% of observation, average onset or late onset. And I'm able to see a statistical difference between the early onset group and the late onset group. Here, what we can interpret from this figure is that if you have this shape, this kind of shape of your hippocampus, which means a thinner tail and a thinner tail, you are developing this hippocampal atrophy later than the one who have this kind of shape of the hippocampus. So concluding now, 3 ideas. There are a lot of longitudinal data sets, and we believe that analyzing those with a dedicated method is necessary. The central part of our method is the X parallelization, which allows to really transport one progression onto another geometry. And the developed method, in the example of Alzheimer's disease, has a potential for automatic diagnosis and prognosis. Thank you very much for listening.
Questions?
It's just a remark. What you called X parallel coordinates in differential geometry are called Fermi coordinates.
All right. Great. All right.
Good man.
So, and I mean, that really means that you have to call it Fermi coordinate.
Okay.
No, I mean,
It's very fancy.
tracking
So.
with Fermi.
Me?
Okay.
Have you considered mapping to looking at high period template for the sub period CA1, CA2, CA3, etc.
I'm sorry, I didn't get it.
The hippocampus
Yeah.
can be divided into sub period
Already?
CA1, CA2, CA3, etc. So they might be able to map the atrophy this particular part.
Okay. Well, I didn't know. I will look into it. So indeed, it could be interesting to have a more specific measure. I guess those divisions have a medical meaning. They have been found by medical doctors.
To look at what the one and I might come and have done and map it to high period template. Maybe the CA1 will atrophy, CA2 will be atrophy. We need to look at that.
Okay. Oh, interesting. Thank you.
Yeah, I have a question about this. Okay, yeah, that's. So the first you have the blue or the blue curve is the geodesic, and you have this direction. So what you could do, I think this is more or less the usual way is to say you will have this direction we have a direction on the evolution for the blue curve, and you will transport. Okay, I'm not clear. Sorry.
No, but I think I see what you
You
would
transport the direction by parallel transport, and you shoot.
Yeah.
So you could do this also. So it could be more or less the same idea, but
So we
I
try.
think it's not equivalent.
No, it's
And
not.
so why are you choosing this point of view? Because this is more robust or whatever?
This is more interesting, we believe, because computing parallel or curves, let's call it parallel curves, this way keep leaves unchanged the variability around the source geodesic. I was not super clear. The source point you are choosing to define the space shift does not influence the parallel curve. Whereas if you are transporting the initial momenta m0 and then shoot, it is very sensitive to the chosen point where you define the space shift. In other words, with this approach, the variability structure, so the distribution of trajectory that we are defining, is not depending on a specific point of the source geodesic.
Okay. So yeah, you say it's changing the okay. Yeah, so this is some problem of stability maybe, no?
I didn't get it, sorry. I don't know.
Can I comment here a little?
Yeah.
I mean, this is certainly the right geometric way, because if you have two Riemannian manifolds and you look at 2 points and you identify the tangent spaces isometrically, if Riemann curvature along these Fermi coordinates correspond to each other, then the two Riemannian manifolds are isometric. So this is the generalization that if curvature is 0, then the thing is isometric to a flat piece. So it really captures all the geometry. So this is certainly the geometrically correct way to parameterize things.
So what is the Fermi coordinate?
Exactly like he.
Yeah, I don't understand. Okay, so maybe this. Two more
It's a
questions.
longer geodesic and you.
Yeah. Oh, okay.
Yeah, it's exactly this thing that is
Okay.
written here.
Two questions, Laurent Karpik, and then we'll move on.
At some point, you say that you were building a finite-dimensional Riemannian manifold of diffeomorphism. It went fast. Is it obvious?
No, it's not obvious. And here I would refer you to the paper of Stanley Durrleman. So morphometry of analytical shape complexes. No, it's not. I went fast indeed.
Is it feasible to just have subject level variables which change over time and into this mode?
Yeah, exactly. At the end, I estimate, like I said, like what I called a space shift, an acceleration factor, and a time shift for each individual. So I have the encoding for the specific distance of this individual to the mean of each of those parameters. And this is how I can look at the distribution and make some statistical tests at the end of my presentation. Here, for example, for each individual, I have a factor alpha I that encodes for the relative speed of development here of hippocampal atrophy. And I can look at this distribution and find that the distribution for the female is different from the difference in mean from the mean of the distribution for the males. I don't know.
Let's thank Alex again.
Thank you very much.